This video covers instrumental variables and their use in dealing with issues of omitted variable bias and endogeneity. So the data we're going to use today comes from the 2000 World Bank Household Survey in Kosovo. So just as a note of caveat, this idea came from an undergraduate econometrics paper. I was interested in the relationship between education and spousal abandonment. So in contrast to some of the more negative literature, particularly in highly developed countries concerning the effects of education for women on marriage, I wanted to see if meeting a certain level of education might actually provide some protection for women against spousal abandonment in war-torn areas such as Kosovo. So the dependent variable in this analysis is abandoned. So 1, the female respondent's spouse no longer lives in the household, and 0 otherwise. Next, I include my basic measure of education, which is literacy. So we can see that not actually an insignificant percentage of these women are not even basically literate. They're not able to read their newspaper. So next I thought I would include age in these models, since it seems that over time in a relationship, spousal abandonment becomes more likely. So I run my first model. Since my dependent variable is dichotomous, I chose a probit model. You can see that age does have a statistically significant effect on spousal abandonment for these women. But contrary to my hypothesis, it was negative, although the coefficient is substantively rather small. So next I include my measure of literacy. And we can see that literacy in this model does not have a statistically significant effect on the probability of spousal abandonment, controlling for age. So it's possible that this effect may be biased. It's likely that there are other things that are correlated with literacy that affect spousal abandonment that haven't been included in this model. There also may be issues with endogeneity. So you can think that education would be endogenous to spousal abandonment. So if a woman thought that her spouse was going to leave, this may make her more likely to get education than she would have otherwise. So one of the first solutions in dealing with endogeneity is to lag the independent variable. So here I generate a lag, my independent variable, and I just lag it by 1 year. So to ensure that literacy is temporally prior to our dependent variable, which is spousal abandonment. Sometimes people will generate lags for multiple years. So that can be done here. You can change this to any value you would like. So next we run our probit model, where we substitute our lagged independent variable for our measure of literacy. And so we can see that the standard errors have gone down significantly, although the variable is still not statistically significant at conventional levels. So probably a better solution would be to include an IVRZ, which meets the following criterion. So first criterion is that the covariance between Z and U should equal 0. And second, our Z, our instrument, and our endogenous X variable should be correlated. So note that you typically cannot test that you've met this first criterion. So what you'll need to do is rely on a theoretical justification for why your instrument is probably unlikely correlated the error term. So the instrument I used in this analysis was the means to get to school. So my thinking was that the means to get to school is very much in the past for these women and is probably unlikely correlated with the present-day probability of spousal abandonment. However, the means that they had to get to school is probably very likely correlated with meeting even a basic threshold of education like literacy. So when we look at the descriptive statistics for this variable, you can see that higher levels of the variable correlate with easier methods of transportation. So if we look at the hours that it took for women to get to school, we can see that hundreds of women actually had an hour or more commute to school. So relying on walking alone would make the journey very difficult for them and make it much less likely that they would get an education. So next we run a regression of our x1, our independent variable that we think is endogenous, and on our z, or on our instrument. And we can see that they are in fact correlated, and this is statistically significant. Our R-squared in this model is rather low, but it is still a correlated measure with our literacy measure, and is statistically significant at over 99.99% confidence level. So next, I'm going to just run a bivariate IVRZ model using my instrument. So we can now see that when we include our instrument variable, our literacy measure, is now statistically significant and has a substantively large negative effect on the probability of spousal abandonment. So literate women are significantly less likely to experience spousal abandonment than are non-literate women. So we can include other covariates in this model, like age. Including the variable after our closed parentheses, which specified our instrumented and variable in our instrument. So we can see in this model that age does not have a statistically significant effect on the probability of spousal abandonment. So it's important to note that although if you think literacy is correlated with the error term, you might think that only the beta coefficient on literacy would be biased. This is actually typically not the case. So long as literacy and age are correlated, then the estimates of the betas for both literacy and age will be biased. So the only way this would be unbiased would be if these two independent variables were not correlated at all. So once we've used our instrumented variable, we have unbiased estimators for our beta for literacy and our betas for age as well. However, if we use a poor instrumental variable, the result is often worse than using no instrument in a typical regression. So our IV is consistent when our Z are instrument and the U are uncorrelated. But if our Z, our instrument, and our X variable are correlated only weakly, this can actually have very serious consequences. And also, if our Z and our U are even moderately correlated, we can have problems. So, if the covariance between Z and X is quite small, we can have issues in using our IV. So I'm going to show you the use of a poor IV and what it can do. So in this case, we're going to use estimated time in residence as our IV for literacy. So estimated time in household residence, we would think this is probably, if anything, very weakly correlated with our X variable, with our measure of literacy. And estimated time in household residence is probably likely correlated with our Y value, our abandoned. So this is going to tell us that the covariance between Z and U is not going to be equal to 0. So this makes our IV a very poor choice. So we can examine this variable. It's categorical, 3 different categories. Next, we're going to include it as our instrument for a measure of literacy. So we could also run this and check to see if in the first stage these two variables are correlated, if our new instrument and our literacy measure are correlated, by specifying comma first. So it reports both stages of the two-stage least squared regression. So we can see in our first stage, our dependent variable here is our endogenous X variable, our literacy measure, and here it's our instrument. The coefficient is rather small. Very importantly, it is not a statistically significant relationship. And our R squared is 0. So this tells us that this is a very poor instrument. If we didn't check for this beforehand and we just went to our results, what we see oftentimes when we use a poor instrument is very large standard errors. So this affects our statistical inferences. So we're much less likely in this case to find statistical significance for our measure of literacy. Also, coefficients sometimes have the reverse sign of what we would expect, which is true in this case. So now we see a positive relationship as suggested by this coefficient between literacy and spousal abandonment, when what we found before was that literacy decreased the probability of spousal abandonment. But again, this isn't statistically significant. So it's very important that you check to see if the endogenous explanatory variable is actually correlated with your IV candidate before you just jump to the second stage of the two-stage least squared regression. Also, another important thing to note is the R-squared statistic. So it's actually possible to get negative R-squared in instrumental variable models. This is because the R-squared value is calculated using the SSR from the instrumented equation. So we have 1 minus SSR over our SST, and so we'd see that this value, this ratio, is going to be greater than 1. So 1 minus a value greater than 1 would give us a negative R-squared value. So the R-squared value that you get in instrumental variables is fairly meaningless, and it also cannot be used to construct your F-tests of joint probability, of joint significance rather. So it's important to note that when evaluating these models. So another issue that we have in this model is due to the fact that our dependent variable is binary. So again, unless all our slope parameters are equal to 0, this means there are going to be issues with heteroscedasticity. So we know the functional form of our heteroscedasticity because we know that in LPM the variance of y conditional on x is equal to p times 1 minus p. So it's going to be important to test for heteroscedasticity in this model. We can run our model and test for heteroscedasticity. So our p-value is less than 0.05, so we can reject our null hypothesis of homoscedasticity. We use Wright's test, which is robust to the form, even though we do know the, at least one form of heteroscedasticity that is going to be present in this model due to the fact that it's binary dependent variable. So then we can treat for heteroscedasticity in a typical way. So we're going to predict our p, and then we are going to recode our p-values so that they land between 0 and 1. And we will generate our weights. So we can actually run our IVRZ with the analytical weight of 1 over h, where h is equal to p times 1 minus p. So when we do this, we see that our literacy measure is actually no longer statistically significant at conventional levels. The sign is still negative. So it demonstrates the importance of correcting for heteroscedasticity properly. I'm going to show you the results when you just run it with comma robust, which includes the robust or white robust standard errors. So when we do this, we find that literacy is actually still statistically significant at a 93.6% confidence level. So That's why it's important to properly model for heteroscedasticity in terms of the inferences you're able to make in your models. So next I'm going to show you how to run IV regressions in R. So this is going to use data from Bosnia, but a similar theoretical backdrop. So to install the IVReg, you're going to run this line of code that I've provided. You should only have to run it once, as long as you don't write over it or clear your workspace. So you also need to call the library car for this IVReg function. So I'll do that and bring in the data. So we run some basic descriptive statistics of our variables of interest. Then we run our first linear probability model. So here age has a statistically significant effect on probability of spousal abandonment. Here literacy does not. So next we can run our IVReg, and the form it takes, you have your dependent variable, your independent variable, you have your endogenous independent variable, and then your instrument. So we can run this. And then it actually tells you to call your results. You can use sum.iv on this object that we've created called iv.i1. You can see it reports the results from our IV model. So another option is IVReg2. So this is an update on IVReg. So it includes a weak identification F statistic, the Wu-Hausman test of endogeneity, and a Sargan test. So it gives you a bit more information about your model. So again, this is the code to install IVReg2. Once I've done that, I can run the model. So this takes a little bit of a different form. We have our y variable. We include our endogenous and independent variable here. That we need to instrument. We include our other covariate as well. So then we specify the variable that is to be instrumented, and here we specify our instrument, and this just tells you to omit missing data in your data frame. So this takes a little bit, so there we go. And so our first stage F test is a weak identification statistic. And so the rule of thumb for this test is that this value should be greater than 10. And this tells us whether the instrumented variable or variables is or are sufficiently correlated with the endogenous variable of interest. So we can say in this case that yes, our instrument is sufficiently correlated with our endogenous variable literacy. So next we report this Wu-Hausman test, which examines the difference between the IV and the OLS coefficients. So if we reject the null hypothesis, this would mean that there is endogeneity. But our p-value is greater than 0.05, so we are unable to reject the null hypothesis. So this actually suggests that our literacy variable is maybe not endogenous. So next, we look at this Sargan test, and in this case it's reporting that no test is performed. And this is because the Sargan test is included in the case of multiple IVs. So a rejection of the null, if we were to include more than one IV, would mean that the instruments are not exclusively affecting the outcome of interest through the endogenous variable literacy. So this is just some basic code on how to conduct instrumental variables in Stata and in R.